The universe is best understood as a giant web. It's a bit hard to wrap your mind around an infinite 3D structure, but if you were to imagine that the universe was laid out flat, it would look like a gigantic spider web stretching into 2D infinity. This cosmic web is made of galaxies and galaxy clusters grouped together in long filaments separated by huge gaps known as voids. Together, they form the largest structures in the universe, spanning hundreds of millions of light years. And while we have a pretty good idea of how they formed, scientists are still working to understand exactly what the cosmic web tells us about the universe as a whole. This web of cosmic filaments may be the key to understanding dark matter and dark energy, to mysterious phenomena that make up a whopping 95% of the universe. We think we know what these things are, but we can't see either of them directly. So astronomers are always looking for ways to learn more. And one of the best ways to do that is to study the cosmic web. Our home galaxy, the Milky Way, lies on one of these filaments, which means that we're surrounded by these enormous voids. In theory, any one of them could hold our galaxy's doom. But don't worry, none of the voids are close enough to affect us yet. Just don't mention that to the Flat Earth Society. It turns out that our own galactic neighborhood is kind of boring. We live in a relatively small galaxy in a region called the local supercluster, which also includes the Andromeda Galaxy and about 50 other smaller galaxies. But outside of this galactic grouping, there are no particularly dense concentrations of galaxies for hundreds of millions of light years in any direction. In other words, we're in a void. It's not just us. Every single one of you watching right now happens to exist within a galactic void, too. You're just not aware of it because we can only see a tiny portion of the night sky at any given time. Most of our local galactic neighborhood is blocked by the sun during the day and by our atmosphere at night. But when astronomers look at the entire sky using powerful telescopes, they see that the universe is divided into a massive web of filaments and voids. Astronomers first noticed these gigantic structures in the 1970s and 80s when they started scanning the skies for quasars. These are supermassive black holes at the centers of galaxies that blast energy out into space at near the speed of light. The brighter a quasar, the farther away it is. Because these beacons of light are so bright, they allow astronomers to peer back through billions of years of cosmic history. That means that when they discovered these incredibly distant quasars, they were seeing them as they existed in the early universe. And by looking at many different quasars, they could get a picture of what the universe looked like at different points in its past. And what they found was that the distribution of galaxies across the universe has changed over time. The key to this discovery was something called the redshift survey. A redshift survey measures the distance to an object by studying how far red or blue shifted an object's light spectrum is. If you hear a car horn approaching you and then passing, you lines notice that the pitch of the horn changes as it goes from approaching you to moving away. This change in pitch is called the Doppler shift. Redshift works in much the same way, except instead of sound waves, we're looking at light waves. If an object is moving away from us, its light waves are stretched, shifting the spectrum towards the red end of the electromagnetic spectrum. The farther away an object is, the faster it's moving away from us and the greater its redshift. Using this method, astronomers can tell how fast an object is receding from us, which allows them to calculate how far away it is. One of the first redshift surveys mapped out the locations of 2,000 galaxies over 600 million parsecs, or about 2 billion light years from Earth. And it revealed something interesting. The galaxies weren't evenly distributed. Instead, they were already starting to form long chains and sheets connected by massive voids. Since then, new redshift surveys have charted even more of the cosmic web, including the Sloan Digital Sky Survey, which mapped over 350,000 galaxies. And more recently, the Abbas survey, which mapped over 40 million. Each new survey reveals more detail of the cosmic web and provides more clues to help scientists understand how it formed. The most recent study to use data from the ABOS survey suggests that the cosmic web grew from a giant web of dark matter that was created shortly after the Big Bang. According to the researchers, the distribution of matter in the early universe would have been slightly lumpy due to quantum fluctuations. As the universe expanded, these quantum fluctuations caused the dark matter to clump together under the force of gravity. Over time, these clumps grew, forming the seeds of the cosmic web. Meanwhile, normal matter would have also been drawn together by the force of gravity, eventually forming the galaxies and galaxy clusters we see today. But while this model fits with a lot of what we know about the universe, it doesn't account for everything. For example, it doesn't explain why some parts of the web have more filaments than others, or why the voids are so big. To figure out what's going on, we need to look at what the voids aren't. You see, the voids between the filaments aren't actually empty. They're filled with gas that's so hot it's nearly impossible to detect. Astronomers have known about this for decades, but they didn't know how much gas was in the voids until recently. In April 2022, a team of researchers reported that they had used data from NASA's Chandra X-ray Observatory to measure the temperature of the gas in 3 of the largest voids in the universe. They found that the gas was extremely hot, ranging between 4 million and 10 million degrees Celsius. At such high temperatures, the gas is ionized, meaning that some of its electrons have been stripped away, making it invisible to most telescopes. But because ionized gas glows brightly in X-rays, Chandra was able to spot it. It turned out that the gas was so hot that it should have been emitting gamma rays instead of X-rays. But to the team's surprise, the voids weren't emitting gamma rays. This suggested that there must have been something heating the gas, keeping it extremely hot. Otherwise, it would have cooled off by now and emitted lower energy X-rays. One possibility is that the gas was heated by a recent collision with another cloud of gas. But the team ruled this out because if the gas had been heated by a collision, it wouldn't have been confined to such a neat spherical shape. Another possibility is that the gas was heated by a large group of galaxies that's invisible to all but the most powerful telescopes. Either way, this discovery suggests that the voids are more complex than astronomers thought, and studying them could reveal more about how the universe evolved after the Big Bang. Besides, we've barely even looked at the voids. All the research we've done so far has focused on the filaments because they where most of the action is. The filaments contain the majority of the universe's galaxies and galaxy clusters, and they're where most of the stars and planets are born. They also contain the majority of the universe's dark matter, which makes sense because dark matter is thought to make up most of the mass in galaxies and galaxy clusters. And since galaxies and galaxy clusters are located on the filaments, it follows that their dark matter halos would be too. Most of the visible matter in the filaments is contained in the galaxies, which come in a variety of shapes and sizes. Elliptical galaxies are smooth and oval-shaped and contain mostly old stars. Spiral galaxies like our own are flat and disc-shaped and contain a mix of old and young stars. And irregular galaxies have no particular shape and also contain a mix of old and young stars. The exact processes that caused these differences aren't fully understood, but they probably have to do with the environment in which the galaxies formed. For example, spiral galaxies are often found in groups or clusters where they're constantly interacting with each other. These interactions may have prevented them from forming a nice smooth shape like elliptical galaxies. Meanwhile, the vast majority of the mass in the filaments is contained in the dark matter halos surrounding the galaxies. These dark matter halos are thought to play a major role in the formation of galaxies and galaxy clusters. They probably helped to hold the visible matter in the filaments together and keep it from drifting away. Scientists are still working to understand exactly how dark matter halos work. But we do know that they're much larger than the galaxies they surround. The dark matter halo of the Milky Way, for example, extends more than 20 times farther out than the galaxy itself. Outside of the filaments are the galaxy clusters. These are groups of galaxies that are held together by their mutual gravitational attraction. Galaxy clusters are the largest gravitationally bound structures in the universe, and they're also some of the hottest. The average temperature of a galaxy cluster is around 70 million degrees Celsius. That's hot enough to melt most metals. The extreme heat comes from the fact that the galaxies in a cluster are so close together. Their gravitational attraction literally heats them up. This heat gives rise to a phenomenon known as weak lensing. As light passes through a galaxy cluster, it gets bent by the gravitational field of the cluster's dark matter halo. This bending distorts the images of the background galaxies, making them look like giant cosmic funhouse mirrors. By studying weak lensing, astronomers can map out the distribution of dark matter in galaxy clusters. They can also use weak lensing to study dark energy. Dark energy is a mysterious force that's causing the expansion of the universe to accelerate. By studying how background galaxies are distorted, astronomers can measure the effects of dark energy on a large scale. And it's not just dark matter and dark energy that make the cosmic web so interesting. It's also home to some of the most extreme objects in the universe, such as quasars and gamma-ray bursts. Quasars are supermassive black holes that feed off of the gas and dust in their host galaxies. As material falls into the black hole, it forms a glowing disk of superheated plasma. This plasma emits light at all wavelengths of the electromagnetic spectrum, making quasars some of the brightest objects in the universe.